My name is Patrick Wardle. I have worked at a variety of acronymed places. Currently the Chief Security Researcher at Synack. So briefly, at Synack we do crowdsourced vulnerability discovery with vetted security researchers. So if you're interested in signing up with us to be a freelance researcher hacker to get paid to find vulnerabilities in our customer web apps, mobile apps, and IoT devices, check out synack.com. All right, so today we're going to be covering a lot of interesting stuff. We're going to start by looking at what happens when an application, which is running at the privilege level of the user, wants to perform a more privileged action. We'll then discuss some core issues with how apps perform this temporary elevation of privileges, and due to these core issues, we'll then show a lot of bugs. We'll talk about how to find these bugs, discuss some actual vulnerabilities, and then end with some exploits. So our goal today is to describe a reliable way to locally escalate privileges. Such privilege escalation is often an essential step that malware wants to accomplish. So again, step one, malware kind of gets on your box. Normally then it's going to be running in somewhat of a constrained environment, or at least at the privilege level of the normal user, not root. So then for step number two, the malware is going to want to escalate its privileges generally to root. So today we're going to be focusing on this second step, step number two, and talk about how to escalate privileges, specifically by exploiting bugs and vulnerabilities in installers and updates. So first, let's look at how an application can authenticate with the operating system to be authorized to temporarily perform high privilege actions. So, if you're a Mac user, I'm sure you're very familiar with these authentication dialogues, as what Apple calls them. We'll also refer to them as authentication or auth prompts. So apps run at user privileges, but sometimes they need to perform higher privilege actions. Most commonly, installers or updaters, they're going to have to write files to a system directory, perhaps update a kernel extension, and obviously this needs to be done at higher privileges. Other actions, for example, debugging another process or even changing operating system settings, such as the time, will often require the user to re-authenticate in order for the application to perform that higher privileged action. So these are quite common. I get about one a day on my box, and if not that, at least a few every week. So first let's look at a conceptual overview of kind of what happens behind the scenes when an application, for example an installer, wants to perform a privileged action. So first it's going to invoke an authentication API. We'll talk about what these are on the next slide. This will generate an XPC message which is sent to the authorization daemon. This daemon then consults the authorization database, and it usually says, okay, I will allow you to perform this action, but first you have to re-authenticate. So it does this by sending another XPC message to the security agent. This agent is then responsible for showing the actual authentication prompt. And then once the user enters the correct credentials and they're validated, the application that requested this higher privilege action is then allowed to perform it. So let's take a closer look at these steps. Again, assume we have an application, for example an installer, that wants to perform a higher privileged action. So it kicks this off usually by invoking something like authorization execute with privileges. And this is a function we'll talk about a lot. You can see on the slides when you invoke this function, you basically just specify a path of what you want to be executed with these higher privileges. And once the user is authenticated, this will then be executed. So if we look at this function, it's open source, we can see it calls execv to execute a setuid system binary named security_auth trampoline. This binary is what sends the XPC message to the authorization daemon authd. We can verify this by using the lsmp utility, which is a utility that can show you sending and receiving of mock messages. All right, so once the authentication daemon, authd, receives this XPC message, which is basically an authorization request, it will consult, as I mentioned, the authorization database. This is in /var/db auth.db. And the system auth trampoline requests the system.privileges.admin write. So we can dump this authorization database, and we can see that privilege exists, and as the comments or the information in the database shows, this is associated with the authorization execute with privilege function, which is what the application just invoked. So again, the authorization daemon's probably going to say, sure, I'll allow you or I'll grant you this privilege temporarily, but first the user's going to have to re-authenticate. So in order to facilitate this, the daemon then sends an XPC message, as I mentioned, to the security agent. So the security agent now has received this XPC message, and it is what displays the authentication dialog. Now this is done by design because Apple didn't want the user to have to trust the application with their password. So since a trusted system utility is displaying this authentication prompt, the application that's requesting the higher privilege actually has no access to the user's actual password. So we can use the ls app info utility and see, yes, security agent is actually the last process that was spawned. And again, this is because it's spawned on demand when it gets these XPC requests from the authentication daemon. It again displays that prompt and handles the verification of the user's credentials. Once the user has verified him or herself, control flow returns back to the security underscore trampoline utility, which via a call to exec v executes the binary that the application originally requested. And again, since this security underscore auth trampoline utility is setuid and is owned by root, the binary or the script that the application requested to be executed will now be executed with root privileges. Okay, so that was a behind the scenes look. What happens again when an application requests or needs to perform some action at a higher privilege level. Now let's talk about how to abuse this process, starting with some core or fundamental issues. So one of the main issues is these pop-ups cannot be easily verified. Anybody can spoof them. They're just a window asking for credentials. So on the left we have a legit pop-up from the Slack application, and on the right, who knows? Is this spoofed? Is this some malware just asking for credentials? Or is it even a legit authentication prompt that was spawned via the security agent but is going to execute something malicious? And what is Slack doing anyways? Like, why does it need to perform a privilege action? So we'll look at some real life examples that abuse this. Again, playing off the fact that the user generally trusts these authentication prompts and they're not easily verified. Now I do want to point out though that these are not, in my opinion, real vulnerabilities. I mean, they're somewhat like UI issues, but when I mentioned to a few people that this is what my talk was going to be about, a lot of people immediately jumped on this. So again, as we'll see, we'll actually talk about some more problematic vulnerabilities, but I wanted to mention this and cover this here. Especially since Mac malware often uses this or abuses this in order to get root credentials. So the first example is a Mac malware called OSX Proton B. What happened was the malware authors or hackers infected the legitimate application website of an application named Handbrake. Handbrake is an open source video transcoder. So again, the hackers accessed that website, got access to the application, infected it with some malicious code. And then anytime moving on in the future, when the users would then download this application, they themselves would become infected. So when the malware runs, the first thing it does is spawns one of these windows. But it doesn't do it through the security agent. It creates its own NS window. So it's 100% fake. But it mimics and looks exactly like a real authentication prompt. However, when the user enters their password, since it's fake, the malware has access to the actual bytes or value of the user's password. So we can see this in a debugger. If we attach to the malware, when the user enters their password, we can see it's present in the malware's memory. And then the malware used this to execute something as root. Now there's also nothing stopping malicious code from creating a real authentication prompt and then get something to be executed as root once the user authenticates. And by real, I mean via these system APIs such as authorization execute with privileges. Again, it's about 3 lines of code, so here's an example how trivial it is to create a legit authentication prompt that will then execute something malicious. If you want to make it malicious but convincing, very easy to do. Here I just grabbed the actual icons from the legitimate Slack application, copied them into my Xcode project. You then set the icon file key in the app's info.plist file, which then will be displayed in this legitimate, albeit malicious, authentication dialog. So if we execute this, a pop-up will be displayed on screen, and it's legit again in the sense that this is being displayed by the system security agent. And since Slack, at least on my box, is popping up this authentication dialog all the time, it's very easy to trick users. And once they enter their credentials, whatever we asked to be executed as root will be. So here's an example of a piece of malware that actually does this, iWorm. So iWorm was distributed via cracked applications on Pirate Bay. So users think that they would be getting, for example, a copy of Photoshop, and they would, but it would also be packaged with iWorm. When the malware was executed, it would invoke the authorization execute with privileged function, which would then display an authentication prompt. Now, users would likely enter their password because, again, there's no way to verify this, and also they're installing software, so they're used to seeing this, especially when they're performing some installer. Now, once the user enters their credentials, the malware executes something named 0, and this will be executed as root. If we look at what that 0 binary does, it persists the malware as a launch daemon, which means the malware will now be always running as root persistently. Now again, malware spoofing or creating these authentication prompts pretty much comes down to social engineering. These are not bugs, these are not vulnerabilities, but they work, so we can't knock it too much. Now I want to talk about some real issues, some fundamental core vulnerabilities. So we've been talking about this authorization execute with privilege API function. The good thing about this API is it's very easy to use. Again, you just specify whatever you want to be executed as root, and then the system will take care of everything else, displaying the authentication prompt, and then when the user verifies and enters his or her credentials, whatever you ask to be executed by root will be by the system. So that's great. The problem is it performs no verification of what it's executing and is open to a massive race condition. So, an example. A legitimate application, say an installer, needs to perform some privilege action, needs to execute something as root. So what it'll do is it'll invoke that authentication execute with privilege function and give it a path to something to execute, for example, an installer script. In the meantime, while the user is entering their credentials, some local malicious code that doesn't have these higher level privileges can actually modify that installation script. And then once the user finishes entering his or her credentials, the system will blindly execute what the app originally requested with no validation or verification that it hasn't been modified or infected in some manner. Another issue is legit applications, imagine they have authenticated securely, and we'll talk about how to do this in a minute, often then do authorized actions that are insecure. So for example, they can persist non-validated components, they can create insecure temporary files, they can even load and execute other non-validated components. So imagine, for an example, there's an installer that's now running as root, it's been authenticated securely and correctly, but then it creates, in the temporary directory, a property list or plist file. A few seconds later, it then moves that plist file out of temp into the system's launch daemon directory, where the launch daemon will be executed as root. Obviously, again, some local non-privileged code can modify that property list while it's in the temporary directory, and then when it's moved into the launch daemon's directory, that local malicious code will have just inherited root permissions. All right, so now let's talk about actually finding some of these bugs. And since we'll see this is such a systemic problem, we're actually only going to look at software that I had installed on my box. So first, let's look at who calls this horribly insecure authorization execute with privilege function. So you can grep the file system looking for binaries that import this. Start maybe by looking at /applications. Or it actually turns out that whenever this API is called, Apple will log this, specifically to the var/log/diagnostic messages logs. Now, unfortunately, these logs are only kept for a few days, but you can start by looking there to see basically who has displayed one of these authentication prompts because they invoked the authorization execute with privileges function. So if we grep or dump these, we can see that pretty much everyone calls this function. Again, on my box, Slack, VMware Fusion, Chrome, Little Snitch, Freedom, Sparkle, everybody. Now, just because someone calls this function doesn't mean it's necessarily an exploitable bug. It's kind of similar to strcpy, right? We know strcpy is like a dangerous API, but if strcpy is used correctly, it doesn't necessarily mean that there's going to be a buffer overflow. An example of a safe use of this function is imagine an installer wants to perform a privileged system command. For example, it wants to execute reboot. Now, obviously, local malicious code can't modify the /sbin reboot utility, right? It's protected with system integrity protection, and et cetera, et cetera, et cetera. So this, for example, is safe. So in order, though, for something to be exploitable, what authorization execute with privileges is about to execute has to be writable, modifiable, and infectable by the local non-privileged code. Turns out, though, this is pretty much always the case. So the question is, how do we tell that what is about to be executed as root is accessible by this local unprivileged code? So the question is, first, what is this going to execute, and then is this writable? So there's two ways to tell or figure out what this function is about to execute. The first is if you use a process monitor utility. I wrote a free one that's open source and will be online after this talk. We can basically look at the arguments to the security_auth trampoline. Again, this is the setUID process that gets invoked when someone calls authorization execute with privileges. So here, for example, we can see it's downloading, or rather going to execute an installer application that's in /downloads. Obviously, local non-privileged code could modify that. Another example is you could basically just debug the process and set a breakpoint on the authorization execute with privilege function, and then look at the arguments, specifically the third argument, RSI, and look at what this is. Again, this will be the path of what is about to be executed as root. And once we know what is about to be executed, we can check the permissions of this file, usually a script or a binary, and if it's owned by the user, which it normally is, this means code that's running as user, not root, can modify this code. And again, once the user then authenticates, we will have root. So later we'll talk also about how apps should securely authorize or authenticate themselves. But as we mentioned, even if they do that securely, if then they execute other actions which themselves are insecure, this still gives us an opportunity to elevate our privileges to root. So in order to find these bugs, pretty much what I do at least is monitor the file system or watch what processes these higher elevated privileged applications will then execute. So again, the question is, can the unprivileged code modify these? Example, a property list that an installer application, it might have in its /resource folder in the downloads directory. It might be authenticated correctly and securely, but then goes to execute that secondary component itself has not been validated. So again, perhaps local malicious code can modify that and get root via that means. All right. Enough with the conceptual blabbering. It's time to talk about some exploitable bugs. In this section, we will talk about the bugs, and then in the next section, how to generically exploit such vulnerabilities. And note, if I don't mention a CVE associated with a vulnerability, it's a 0-day or a bug that the vendor has decided not to patch. So the first bug is in a popular IoT device, one that I use, Dropcam. Basically, when you buy a new Dropcam and you go to configure it, the instructions say plug it into the computer. This will mount something on a drive. Double click that, which is the installer application, and then follow the authentication prompt and it will install and configure the Dropcam for you, basically setting up the Wi-Fi networks, etc. for the IoT device. So it turns out, though, when it executes this application off this mounted share, what it does, it makes a copy of the installer application into the user's temporary directory. It then executes this via the authorization execute with privilege function in order to execute that with root privileges. So what we can do is we can attach to this process with the debugger. Here we use LLDB. We set a breakpoint on the authorization execute with privilege function. And when we hit this breakpoint, we can dump the third argument, again RSI, and this is the path to what is about to be executed with root privileges. And again, we can see it's the installer application that has been copied into the user's temporary directory. Now again, there's a large window of time when the user is legitimately authenticating where local malicious code could modify that installer application in the temporary directory. And again, since the authorization execute with privilege function does not validate what is about to be executed, as soon as the user completes the authentication, our malicious code will be executed now with root privileges. Next is Chrome. This is a rather popular browser that I use on my box. It also invokes the authorization execute with privilege function in a variety of instances. For example, if you're installing it as a non-admin user, or if you're setting things up like auto updates. So we can observe this by running our process monitor, and again we see that security_auth trampoline process, and if we look at what that is about to execute as root, we can see it's a script named keystone_promote_preflight.sh. This script, which again is run as root once the user authenticates, is owned by a normal user. So this means at any point, any local non-root code on your box could modify that. And then when the user performs, for example, sets up an auto update, Chrome will blindly execute that as root. Next up is Little Snitch. This is everyone's firewall on macOS, something I used to run until I wrote my own. Unfortunately, their installer had a local privilege escalation. And this is an example of something that authenticates correctly, but then performs malicious actions that then non-privileged local code could leverage to elevate its privileges to root. So the issue was the authorized installer, which again is running as root, wrote a property list to the temporary directory. It then moved that into the launch daemons directory where it would be loaded and executed as root. So again, what local privileged code could do was modify that property list when it was in the world writable temporary directory, and then it was moved into the system launch daemon directory and executed, the malicious code would get root. So if we take a closer look at this bug, on the screen at the top right, we can see the little snitch installer calls something write plist owner mode to file. And we can see this calls the ns temporary directory function to get the user's temporary directory and write out what will be the launch daemons property list. So what we can do is we can attach a debugger to the installer and then set a breakpoint on the method execute command as root. And when we can see what this command is then doing is moving the plist from the temporary directory into the system launch daemon directory and then setting it to be owned as root. Obviously, again, while this is in temp, a user who doesn't have correct privileges or some malicious malware could modify that, and then it would be execute with higher privileges to root. Little Snitch actually patched this really quickly, so kudos on their response, as CVE 2017-2675. I also do a lot of malware analysis, so I use VMware. So whenever you go to install VMware, or when it tells you that there's an update, what it does is it saves various scripts into the user's temporary directory, and then executes them as root via the authorization execute with privileges functions. So we can see this by debugging the VMware installer or updater. Again, you set a breakpoint on the authorization execute with privileges function, and then when the breakpoint is hit, dump the third arg, and you can see what's being executed. Again, it's these scripts that are out of the world writable temp directory. Again, nothing is verified, so these will then be executed as root. All right, more security software. Yes, this is the VPN I run, F-Secure's Freedome. Turns out it is vulnerable as well. So when you install this VPN, it tells you, hey, I'm about to show you a pop-up, please enter your credentials. And then when this pop-up is displayed, it doesn't actually say Freedome is doing it, it says something named OSA script, which is Apple script. So I wondered, what is Apple script executing? So if you disassemble Freedome, we have some disassembly on the slide, we can see it's executing an Apple script to authenticate and then execute something as root via the do shell script with admin privs. This then calls Apple script to display an authentication prompt, and when the user enters their credentials, whatever was requested is executed as root. So our process monitor shows that the Apple script is executing a script in the applications bundle, which is of course writable or modifiable by local non-privileged code. Next up is Sophos. Yes, due to work compliance, I have to run antivirus on my computer. My boss told me though if I found a vulnerability in it, I could uninstall it. So this was kind of the motivation for that. Gonna hold them to that. So when you download Sophos, it's a zip file. When you unzip it, it executes an installer application. And you guess this then in turn executes a secondary component via the authorization execute with privileges. And we can dump via the debugger what's it about to execute, and it's something called installation.deployer. Again, if there's some malicious code on the box that has not root privileges, it can modify this component, and then that will be executed as root. All right, finally, we've got Sparkle. Now, Sparkle is an auto-update library that's used in a good number of apps. Now, I do want to point out this is merely a list of apps from 2016 that use Sparkle. I have not validated if these are all vulnerable. I just wanted a list. Let's look at an example or specific instance of an application that uses Sparkle that is vulnerable. So I do a lot of reverse engineering. I use hopper.app occasionally. It's a nice app. Anytime it has an update or a new version, the Sparkle library that's compiled in displays this pop-up telling me that there's a new version. If we click on it, Sparkle will download something called autoupdate.app into a non-protected cache directory. It then executes this. Now, depending on the user's permissions, for example, if they're a standard user versus an admin user, this will display an authentication prompt. If we view this in a debugger attaching to the auto update process, set a breakpoint on authorization execute with privileges, we can see it's trying to execute something named file op out of a user writable cache directory. Again, if there's any local non-privileged code, it can obviously modify anything in this cache directory, and then that will be executed by root when Sparkle completes the update process. All right, enough knocking on third-party apps. I think by this time we understand that the authorization execute with privilege function is, shitty, don't use it, but everyone pretty much does. So I want to talk about some issues in Apple's code now. They're not safe from these issues either. So the first thing is, I'm not really sure if this is a bug, it's more of a silly issue, but when a user drags something via Finder into a higher privileged directory, the finder.app displays an authentication prompt, basically saying, hey, you need to provide correct creds in order for me to complete this copy action. The problem is, it doesn't validate that what the user originally meant to copy wasn't modified during the time they were authenticating. So we can imagine a scenario where a user is trying to move an app, for example, into /applications. They have to provide their credentials. Again, some local unprivileged code could perhaps modify what they were moving into applications, and then the move would still succeed, and now they've just got some malicious code into a higher privileged directory, which might be executed by other users. All right, something though that I think is a real issue. So Apple's package installer is called installer.app. Basically, when you double-click on a PKG file, installer.app will be automatically executed to handle the installation of this package. And why does this happen? Well, if we dump the info.plist file of the installer.app, we can see it advertises as the default handler for packages. Note also, it's a signed utility via Apple, and also has some special privileges or entitlements. So here's an example when, again, a user double-clicks on a PKG file, installer.app will be executed to handle that. It will display this nice installation prompt and then request user permissions. Again, this is all just standard stuff. I took a closer look at this process and realized that this signed trusted installer.application would load dynamic libraries from /temp. I have no idea why. Now, we'll talk shortly about weaponizing this, but let's look at what is going on. So when the user double-clicks on a PKG file that has a plugins directory, installer.app would take those plugins, copy them into the user's directory, and then load them into its trusted process context. In a debugger, we can set a breakpoint on DLOpen in the installer.application, and then we can dump what is about to be loaded, and we can see, yes, it's about to actually load an unsigned dynamic library from the user's temporary directory. You could also use an application like Task Explorer, which I wrote. We can filter on unsigned dynamic libraries and see, yep, there is an unsigned dynamic library loaded from the temporary directory. All right, so that's about 1,000 ways to get root, but what if you want more? And not because we're greedy, but on recent versions of macOS, you actually are still somewhat limited when you have root permissions. You can't bypass system integrity protection to modify operating system components, and you can also not run unsigned code in the kernel. So the bugs I found that I'm going to talk about here need root in order to trigger, but once you then exploit these vulnerabilities, you have these even higher privileges. So the first bug allows us to bypass system integrity protection and also survive a full OS upgrade. This is something that malware would like to do. All right, so it's time to upgrade. What happens is the user will download the OS update from the App Store. Long story short, an entitled binary named OSI helper D will tell the system to boot off an installer image, install esd.dmg. This is what is downloaded from the App Store. And then this is when the system reboots what actually installs the new version of the operating system. So our goal is to get into this installer image because once the system has booted off it, we are essentially booting or executing outside the context of the operating system. So operating system level protections such as system integrity protection are no longer in play. So Apple generically realized this attack vector, well, that is to say blessing off an untrusted disk image, so they block that ability unless you have the correct entitlements, which an Apple utility such as OSIS helper D has. So step one is to get a dylib into the OS installer application, which is downloaded from the App Store when the user wants to perform an upgrade. And we can use a neat runtime dylib injection technique, which I like to call dylib proxying. Basically what you do is you replace a dynamic library that the application is dependent on, and then proxy requests to the original one as not to break any system functionality. And then when that application is executed, the dynamic loader will naively and blindly load the malicious dylib in place. This was a technique that was used in some Israeli malware on the Windows platform. I haven't seen it used on the Mac operating system. I'm not sure why. Kind of a neat technique. All right, so now we have code executed in the trusted context of the operating system installer application. So what we can do now is modify or infect the install ESD disk image. And then the OSIS helper D blesses it. Oops, there's no validation that what it's about to bless has not been tampered with. So now the system reboots. We are running in the process context outside the operating system. And so we can obviously bypass system integrity protection and ensure also that our malware fully lives or survives through a full OS upgrade. So as a proof of concept, I took iWorm, which is a well-known piece of malware that we talked about earlier, and injected this into the installation image. And then during this install process, I copied it into a system integrity protected directory, which means that once the OS install upgrade completed, that malware was essentially undeletable. Apple fixed this as CVE 2017-6974. All right, what about a pure kernel bug? Again, our goal is to get unsigned arbitrary code running in the context of the kernel. Again, root for this bug is a prerequisite, but we showed a lot of ways to get root privileges, so that's okay. So I stumbled across this bug. I was writing some code that used the audit subsystem, and I noticed there was an interesting bcopy. So bcopy is essentially a memcopy, copies something from source to destination by some number of bytes. Here we can see the bcopy source is a sock adder struct named SA. Destination is a sock adder underscore storage named arg sock adder. And its max size of the destination buffer is 128. Now, interestingly, the number of bytes that are copied is the size of the sock adder source structure. So anytime you see a bcopy where it's using the number of bytes to copy based on the source, always take a closer look at that. So we know the destination object is of max size 128. So the question then becomes, can we make the source object, a sock adder structure, bigger than that? Turns out the answer is yes. We can create a Unix socket that has a path which allows us to create a socket structure that's bigger than 128 bytes. So what we do is we create that and then we call bind, which will trigger the vulnerable bcopy because it's trying to audit that socket operation. And via the diagram, we can see that since the sock adder structure is bigger than 128, this will cause a heap overflow. For example, here we can see the 41, 41, 41 is now in a kernel pointer we control. So exploiting this bug will give us arbitrary unsigned code execution in the context of the kernel. All right, so that was a good deal of bugs, but what good are bugs if we can't exploit them? So let's talk about now how to exploit such vulnerabilities. All right, so again, back to the user-assisted elevation of privileges. A goal is to get root when a vulnerable but legitimate application invokes or displays an authentication prompt. So as a limited process or limited local code, to do the exploit, we have to do three things. We have to wait for a vulnerable application to start, VMware, Sophos, Sparkle, Little Snitch, whatever. Then we have to wait for it to perform an insecure authentication request. And then while the user is entering their credentials, quickly infect the vulnerable file. And then as soon as the user completes the authentication, we will have root. So step one, we need to monitor for the execution of these vulnerable applications. Turns out this is really easy to do. You don't have to have special privileges. You can use the NS Workspace Notification Center and register a notification for application launches and exits. So in our notification handler, we bail if it's an application that's not of interest, for example, calculator. But if it is, for example, it's Sophos, VMware, one of the myriad of other applications we talked about, we move on to step two, which is monitoring for the vulnerable file to be created. We also care about application exits because we want to stop monitoring once the application exits. Okay, so as non-privileged code, you can watch for specific files or directories using FS events. So here's some code where we watch for a target file. Now this will be application specific. For Little Snitch, for example, it's a property list in the user's temporary directory. For Freedom, it's a script in their application bundle. For Sparkle, it's the auto update application that's downloaded. Either way though, we can detect when these vulnerable files are created. And once we get a callback in our callback handler, we know it's go time. Let's go infect. All right, so now we've seen the file has been created. Again, once the user authenticates, this will be executed as root with no verification. So we mentioned again, this file will be application specific, so this dictates the infection technique. So for example, for a property list or plist file, we're probably going to modify the program arguments array and point it to a malicious binary. For a script, you can just infect it by adding some extra commands that you want to be executed as root. And if it's going to execute a macOS binary as root, you can either infect that or you can actually just replace it with your own binary, and again, that will be executed as root. And a very valid question is, don't we have to win a race? And the answer is yes. So again, the application is usually going to drop whatever it wants to execute as root, then throw up the authentication prompt, and then while the user is authenticating, we can jump in and infect that. So this user authentication usually takes at least 1 or 2 seconds, and that's a massive window that we can always win. Now, a prerequisite of this exploitation is that this non-privileged local malicious code has to have the ability to write to the item that's about to be executed, right? If it's non-writable, we can't modify it or touch it. This is usually just an issue, not because we don't have the correct permissions, but because of what is about to be executed is on a read-only share. So one example is due to Gatekeeper. So I found a bunch of issues with Gatekeeper, and the way Apple fixed them is to implement something called app translocation. Basically now on modern versions of Mac OS X, if you download a zip file from the internet, when you go to double click and unzip and execute the app within it, it's transparently copied to a read-only share and executed from that share. And this is to deal with a bunch of Gatekeeper issues. This read-only is bad for us because imagine that application is executing something in its application bundle as root. Now it's sitting on this read-only share, so we can't modify that anymore. Well, it turns out this is pretty easy to bypass. Again, if you're local non-privileged code, you can just remove the quarantine attribute from that downloaded zip file, and then app translocation won't happen. The application will remain in the downloads directory, and you can modify it as much as you want. Recall also Apple's installation.app, which is the default handler for PKGs, can be coerced into loading unsigned malicious dilibs. What if the package, though, doesn't have plugins? Well, it would be great if we could basically infect arbitrary PKG files. So normally PKG files are distributed on disk images, DMGs. And when you double click a DMG, it's mounted but on a read-only share. So again, this is problematic for us. What we can do, though, is as local non-privileged code, we can register to be the default handler for DMG images. Then when the user double clicks on that, it'll execute our code, and we can then force that DMG to be mounted with read-write privileges. We can then modify that package, inject a malicious plugin, and then when the user double clicks on that, that malicious unsigned dynamic library will be loaded into the trusted process context of Apple's installation application. All right, so that was generically how to exploit some vulnerabilities and how to deal with read-only issues. Let's now look at some actual exploits. So demo time, here we have VMware. It's telling us to do an update, and we're good users, so we know that when an application requests an update, we should listen because it's going to patch security fixes and give us all these great new features. So in the demo, we'll see the exploiter utility, which is running with normal low-level privileges. It's going to detect that VMware is running. It's going to register a file watch for the scripts that VMware drops into the temporary directory and then infects those scripts. And then when the updater completes by asking the user to please provide their credentials, we will pop calc as root. So watch closely. We're waiting for VMware. We see VMware is running. We detected that the script is about to be present. In a second, infect that. VMware legitimately asks for creds via the authentication execute with privilege function. As soon as that executes, whatever VMware asked to be executed, which were scripts out of the temp directory, are now executed as root. And again, there's no verification on these, so we've popped calc as root. Here's an, yes. I saw a funny tweet. It was like, clap at DEF CON if you see calculator running. So, got to use calc, even on Mac. So here's another demo with Chrome. This is pretty much the simplest, stupidest exploit ever. Basically, you have a Python script that's running as a non-privileged user, and it's going to infect that script that Chrome runs or requests to be run with root privileges. Again, Chrome asks the user to authenticate, and they do. We'll be able to pop calc. Really, the hardest thing here was to basically get calc to run as root. So we run our Python script. It infects that script because we have the right privileges. Chrome asks the user to authenticate because they want to execute the script as root. Again, there's no validation, so then Chrome executes the script as root, which we've infected to execute calc. Again, Chrome said, we're not going to fix this. Finally, let's talk about exploiting Apple's installer. And I think this is kind of my favorite. Why? It's because people use installer.app all the time. And what we can do is basically inject malicious code, unsigned dynamic libraries, into the package that is about to be installed, and then installer.application will load them. So in 3 steps, we basically expand the PKG, inject our malicious dilibs into it, repackage it up, and then when the user double clicks to execute this, installer.app will load our malicious unsigned dilibs into its process context. So now we're running within installer.app. So what can we do here? Well, we can either display our own authentication prompt, which everyone will trust because it's the installer application displaying an authentication prompt, which is what it always does anyways. Or to be even more stealthy, we can just wait until installer.app requests the user to authenticate anyway, and then piggyback off that. I reported this to Apple via their bug reporting website, got no response. Maybe they're just sick of hearing from me. Probably. They don't really like me. All right, so let's start by end by wrapping this all up. So hopefully you have a healthy paranoia of these authentication prompts. I do. Why? First, they can be spoofed. Like, there's no way really to easily validate that this is not completely fake. And even if it is a legitimate, pop-up that the security agent has displayed, like, how do you know what it's about to execute? And again, every freaking application invokes this insecure API, meaning local code that's on your box, if it wants to elevate its privileges to root, can very, very easily infect that. So if you're a malware author, stop spoofing these boxes. Like, it's really lame. Like, do something a little cooler. I'm getting bored as a Mac analyst. Malware analyst is seeing these. Amit knows what I'm talking about. He complains to me all the time. So instead, be patient. Wait till one of these vulnerable applications, which is pretty much most applications, needs to perform an upgrade or is installed. And again, what you can then do is piggyback into that, and then when the user authenticates, you will have root. Again, a lot more stealthy, a lot more elegant. So what is the answer? Well, the answer is to use smjobbless. This is an API that was recently introduced by Apple, and it does allow you or applications to do secure authentication, but it's incredibly complicated. So what you have to do is put whatever you want to be executed as root, this is called the helper tool, in the contents/library/launch services directory. Then in your application's info.plist file, you have to identify the signing information of the helper tool. Then you invoke smjobbless, which will cause the service management daemon to copy your helper application into a secure location. Then, in that secure location, it is cryptographically verified that it hasn't been tampered with. Only then, once that verification is validated, it's copied to the system launch daemon directory and executed as root via a launch daemon. So here's code to do it. You can see it's actually not too complex in code once you get everything set up. And again, this will allow you to securely install and execute something with higher privileges that local malicious code cannot tamper with. So why aren't people using it? Why is Chrome, VMware, Sophos, Little Snitch, why is everyone using the insecure variant? Well, first, your application has to be signed, which means you have to give Apple $99 a year. Also, you can't specify command line arguments. You can't pass command line arguments to whatever you're about to execute. You can use XPC, but this is kind of a pain in the butt. I consider myself a decent coder. It took me hours to get working. And also then it persistently installs something as a launch daemon. This is like massive overkill if all you want to do is run a simple installation script. And then there's kind of a catch-22. This, launch agent has been installed and running as root. Your app can't actually now uninstall it because it's running with higher privileges. So again, you have to set up this XPC channel or tell the launch daemon to uninstall itself. It's just incredibly complicated and usually way overkill. All right, so before we end, I assume you're at this talk because you're somewhat interested in Mac security. Shameless plug for my Mac security website. But everything here is free, so I hope this doesn't sound like a sales pitch. In my free time, I like to write security tools, blog about this kind of stuff, write about a lot of malware analysis, etc. So if you're interested in this stuff, check it out. All right, well, that's a wrap. Again, thank you so much for attending my talk. And again, if you're interested in being a security researcher with Synack, check out synack.com or come chat with me. So if there's any questions, or I'll be here afterwards, I'd love to chat with you more about this. Thank you.